Welcome to the module Introduction to Motion Simulation and Forces. In this module, you will learn how to create a motion study, add a motor to the assembly, add a load, calculate the motion study, and plot the results. In this module, you will learn how to create a motion study to animate the motion of an assembly and use SolidWorks Motion to simulate physical behavior of a car jack. You will also learn how to determine the torque and power required to lift a vehicle. This module is divided into several topics. Click the topic titles in the list for a brief overview of each topic. In this module, you will perform a basic motion analysis using SolidWorks Motion to simulate the weight of a vehicle on the jack and determine the torque required to lift it. Engineers can then use this information to choose the required electric motor to drive the car jack. A mechanical jack is a device that lifts heavy equipment. The most common form is a car jack, floor jack, or garage jack, which lifts vehicles so that maintenance can be performed. Car jacks usually use mechanical advantage to allow a human to lift the vehicle. More powerful jacks use hydraulic power to provide more lift over greater distances. Mechanical jacks are usually rated for a maximum lifting capacity, for example, 1.5 tons or 3 tons. Since this is our first motion analysis, no contact is used and the tilting motion of the jack is prevented with the help of the mates. Click the arrowheads along each edge of the content frame to move to the next slide. The car jack will be driven at a rate of 100 RPM and will be loaded with a force of 8,900 newtons, representing the weight of a vehicle. We can determine the torque and power required to lift the load from the range of motion of the jack. The solution to the defined problem is divided into creating a motion study, adding a rotary motor, adding gravity, adding the weight of the car, calculating the motion, and plotting the results. Let us see how to create a motion study. Click Show Me to launch a demonstration video. Before proceeding, we need to activate the SolidWorks Motion add-ins. Click Tools. Click Add-ins. And click Active Add-ins and Startup checkboxes for SolidWorks Motion. Click OK. Open the car jack assembly from the Lesson 1 Case Studies folder. Click File, and then click Open. Select the car jack assembly. Click Open. SolidWorks Motion uses the document units set in the SolidWorks document properties. Click Options. Click Document Properties. And then click Units. Ensure that MMGS is selected as the unit system. This will set our length units to millimeters and force to Newton. Click OK. Click on the Motion Study 1 tab that appears at the bottom left-hand corner of the window. If this tab is not visible, click View, User Interface, and Motion Manager. Click the Type of Study drop-down. We can see there are 3 types of studies: animation, basic motion, and motion analysis. An animation is used to create animations for illustration purposes. A basic motion analysis can be used to create animations where gravity, mass, and collisions are applied to the parts in the model. Motion analysis is a complete rigid body simulation environment used to obtain numerically accurate, physics-based data and animations. Click Motion Analysis from the list of available study types. That brings us to the end of this demonstration. Click Next to continue. Now you take the controls and find out how much you have learned about creating a motion study. Click Try It to launch the simulation and go through the steps on your own. Congratulations! You have successfully completed this simulation. Click Next to continue. Here's a question to check your understanding of what has been covered so far. Motion can be driven by motors, gravity, forces, and springs. Each one has different characteristics that can be controlled. Motors can create either linear, rotary, or path-dependent motion or prevent motion. This motion can be defined in a number of different ways. Constant speed. The motor will drive at a constant velocity. Distance. The motor will move for a fixed distance or degrees. Oscillating. The motor will have a to and fro motion at a specific distance at a specified frequency. Segments. Motion profile is constructed from segments of the most commonly used functions such as linear, polynomial, half-sine, and others. Data points. Interpolated motion is driven by a tabular set of values. Expression. The motor can be driven by a function created from existing variables and constants. Servo motor. The motor that is used to implement control actions for the event-based triggered motion. Gravity is an important quantity when the weight of a part has an influence on its simulated motion, such as a body in freefall. In SolidWorks Motion, gravity consists of two components. 1. Direction of the gravitational vector, and 2. Magnitude of the gravitational acceleration. The gravity parameters allow you to specify the direction and magnitude of the gravitational vector. You can specify the gravitational vector by selecting the x, y, and z direction or by specifying a reference plane. The magnitude must be entered separately. The default value for the gravitational vector is z, and the magnitude is 9806.55 millimeters per second square, or the equivalent in the currently active units. Forces in SolidWorks Motion can be divided into two basic groups: action forces and action and reaction forces. Action forces are a single applied force or moment, representing the effect of the external objects and loadings on the part or subassembly. The weight of the vehicle applied on the car jack or an aerodynamic force on the car body is an example of action forces. Action and reaction forces are a pair of forces or moments. Both action and corresponding reaction are applied on the parts or subassemblies. A spring force is an example of action and reaction force because the forces on both ends of the spring are on the same line of action. Click the arrowheads along each edge of the content frame to move to the next slide. Applied forces are forces that define loads at specific locations on a part. You must provide your own description of the force behavior by specifying a constant force value or a function expression. The applied forces available in SolidWorks Motion are applied force, applied torque, action-reaction force, and action-reaction torque. Applied forces are used to model inputs such as actuators, rockets, aerodynamic loads, and many more. The orientation of action-only forces can be fixed or relative to the orientation of any part in the mechanism. To define a force, the following information must be specified: part or parts on which the force acts and point of the force application, magnitude and the direction of the force. The force direction is based on the reference part you select in the force direction box. Based on selecting the reference component, there can be 3 cases on how the force direction changes. Case 1. Direction of the force is based on a fixed component. If the fixed component is the assembly origin, then the initial orientation of the force will be held constant throughout the simulation. Case 2. Direction of force is based on the selected moving component, which is also the component on which you want to apply the force. If the force is applied to the part used as the reference datum, then the force will remain locked in its relative orientation to the body over the entire simulation time. That is, it will stay in alignment with the geometry on the body used to define the direction. Case 3. Direction of force is based on the selected moving component, which is different from the component on which you want to apply the force. If another moving part is used as the reference datum, the direction of the force will change based on the relative orientation of the reference body to the moving body. This is hard to visualize, but if you apply the force on a body that is held locked in position and use a rotating part as the reference datum, you should see the force rotate in concert with the reference body. Let us see how to create a motor and apply gravity and forces. Click Show Me to launch a demonstration video. We will create a motor that will spin at 100 revolutions per minute and act on the screw rod part to lift the jack. Click Motor. Ensure that motor type is set to rotary motor. Under Component Direction, select the cylindrical face of the screw rod. The motion direction field will automatically populate the same face to specify the direction. An arrow appears on the surface of the screw rod part. This arrow indicates the direction the motor will spin. In this case, we want the motor to spin in the opposite direction as shown. Click Reverse Direction to orient the motor. Leave the Component to Move Relative to field empty. This ensures that the motor direction is specified with respect to the global coordinate system. Under Motion, ensure that constant speed is selected and enter a value of 100 RPM. Click the graph in the Property Manager to view the enlarged plot. The plot shows that the motor will spin at a constant rate of 100 revolutions per minute throughout the simulation. Click OK. Click Gravity. Under Gravity Parameters Direction Reference, click Y. The arrow in the lower right-hand corner of the viewpoint indicates the direction of gravity. Under Numeric Gravity Value, keep the default value as it is and click OK. Click Force. The force will act on the top of the jack and simulate the weight of a vehicle. For type, ensure that force is selected. Under Direction, ensure that Action Only is selected. Under Action Part and Point of Application of Action, select the circular edge on Component Support 1. The reason why the circular edge can be selected in this circumstance as opposed to the top surface is because this is a rigid body system. A force can be applied to any entity of a rigid body because rigid bodies, by their nature, don't deform. For force direction, select the vertical edge on the base 1 component. Ensure that the load is acting in the downward direction. Under Force function, ensure that Constant is selected. Enter a force value of 8,900 Newton. Click OK. Click Calculate. The simulation will calculate for 5 seconds. 5 seconds is the default simulation time for a motion analysis. However, the simulation time can be edited. Drag the end time key to 8 seconds on the timeline. Click Calculate. This time simulation will calculate for 8 seconds. That brings us to the end of this demonstration. Click Next to continue. Now you take the controls and find out how much you have learned about creating a motor and applying gravity and forces. Click Try It to launch the simulation and go through the steps on your own. Congratulations! You have successfully completed this simulation. Click Next to continue. Here's a question to check your understanding of what has been covered so far. The primary output from a motion study is a plot of one parameter versus another, usually time. Once the motion is calculated, plots can be created for a variety of parameters. All existing plots will be listed at the bottom of the Motion Manager tree. Plots of the following categories can be created: displacement, velocity, acceleration, forces, momentum, energy, power, and other quantities. Further, each category has a list of subcategories. Let's see how to plot results. Click Show Me to launch a demonstration video. We will start by creating a plot of the torque required by the motor to lift the jack. Remember, the motor was defined to spin at a constant rate, 100 revolutions per minute. In SolidWorks Motion, the motor will generate whatever torque necessary to maintain the specified speed. Click Results and Plots. We will create a plot of required torque versus time. Click the Result drop-down, and then click Forces. Under Subcategory, click Motor Torque. Under Result Component, click Magnitude. Under Select Rotational Motor Object to create result, select the motor that we created previously. Once the rotary motor 1 is selected, a triad is displayed in the graphics area. This triad indicates the local X, Y, and Z axes of the motor in which the output quantities may be displayed. In the present case, we require the plot of the magnitude, which is independent of the coordinate system. The post-processing is described in greater detail in the next module. Click OK. The plot of torque required appears in the graphics area. The required torque is about 7,244 Newton-millimeter at its peak. The torque decreases with time because, as the lift moves, the mechanical advantage increases. Now, we will plot the power consumed to lift a weight of 8,900 newtons. We will add the plot power consumption into the existing plot of motor torque. Click Results and Plots. Under Result, click Momentum, Energy, Power. Under Subcategory, click Power Consumption. Under Select Motor Object to create result, select the same motor that you selected in the previous step. Under Plot Results, click Add to Existing Plot and, from the drop-down, select Plot 1. Click OK. The power consumption is 76 watts. Based on the torque and the power information, we can select an electric motor and use it to drive the screw rod instead of a human hand. Click Play. The vertical time bar in both the Motion Manager and the graph indicates the time. Click Stop. Close Plot 1. That brings us to the end of this demonstration. Click Next to continue. Now you take the controls and find out how much you have learned about plotting results. Click Try It to launch the simulation and go through the steps on your own. Congratulations! You have successfully completed this simulation. Click Next to continue. Let us see how to plot the vertical position of the support. Click Show Me to launch a demonstration video. Click Results and Plots. Under Result, click Displacement, Velocity, Acceleration. Under Subcategory, click Linear Displacement. Under Result Component, click Y Component. For Select 2 Points or Faces, select the top face of the support. If no second item is selected, the ground serves as the default second component or the reference. Leave the Component to Define XYZ Directions field empty. This indicates that the displacement is reported in the default global coordinate system. Click OK. The graph indicates change of the global y coordinate of the origin of the support part. The displacement is therefore 51 millimeters, that is, 212 to 161 millimeters in the positive global y-axis. We will modify the plot so that the x-axis is no longer time. Rather, the x-axis will display the angle of the motor. Scroll down in the Motion Manager tree and expand the Results folder. Right-click Plot to and click Edit feature. Click the drop-down menu under Plot Result and click New Result. For Define New Result, click Displacement, Velocity, Acceleration. Under Subcategory, click Angular Displacement. Select Magnitude for Result Component. Click Rotary Motor 1 for the simulation element. Click OK. The result plot is a little coarse, and the data ordinate does not cover the full range of -180 to 180 degrees. To generate a graph with finer detail, more data must be saved to the disk. That brings us to the end of this demonstration. Click Next to continue. Now you take the controls and find out how much you have learned about plotting the vertical position of the support. Click Try It to launch the simulation and go through the steps on your own. Congratulations! You have successfully completed this simulation. Click Next to continue. SolidWorks Motion has its own set of properties to control the way the study is calculated and displayed. Study properties will be discussed throughout the course. Here, we will talk about a specific option in the motion study properties that is frames per second. The frames per second parameter controls how many frames are calculated by the solver. SolidWorks Motion has its own set of properties to control the way the study is calculated and displayed. Study properties will be discussed throughout the course. Frames per second controls how often the data is saved on the disk. The higher the frames per second, the more dense the data recorded. Let's see how to change the frames per second. Click Demonstration to see how this is done. The ordinate of the existing plot does not cover the full range of -180 to 180 degrees. Also, the plot is a little coarse, so we need to generate a plot with finer details. Click Motion Study Properties. Change the frames per second to 100. Click OK. Click Calculate. Notice that we have more details and the angular displacement is nearly from -180 to 180 degrees. Save and close the file. That brings us to the end of this demonstration. Click Next to continue. Here's a question to check your understanding of what has been covered so far. You've reached the end of the module, Introduction to Motion Simulation and Forces. Here are the key takeaways from the module. Click each tab to learn more. Here is a chance for you to practice what you have learned. Offline exercises are available for this module. To attempt these exercises, you must have access to a SolidWorks installation. To complete each exercise, download the self-extracting executable file from the eCourse Details page on mysolidworks.com. This file contains the sample models and exercise PDF file for every module in the eCourse.